basically, we are QPQ International is a platform and deal advisory focused on helping green energy project developers get funding on optimal terms, whether it's be debt or equity, with over 650 investors as of today, and a team of 32 people. We and a pipeline of over 200 projects, with at least 60 projects that are in discussions with investors, and at least like 20% of that is in the pre-closing or closing stages, and at least half of that is not 200 projects, but those that are ready now, like 60 at least, in a serious discussion or due diligence with investors. Yes, so that keeps our team busy, even in summertime. With our full commitment is to work with developers to solve their challenges, help them to achieve their dreams, goals, and ambitions. And we are proudly can say that as of today, we work with over 850 professional developers. This series are organized as our way to add value and emphasis on, and it's our funding accelerator program that's kind of been going for some time. We invite experts, and our emphasis is very much peer-to-peer learning. We invite experts, people who really not academics or policymakers, but people who really kind of got their hands dirty with real experience in the field, and succeeded and failed and made great, wonderful things, and had great professional journeys in this. And all of you know that all of you who've been in this industry for a while, we know there has been a difficult, challenging times for those who were early kind of movers and started in this industry early, say from beginning of 2000s, expecting that the world will be moving logically as it should. And then a lot of people, of course, got burnt, a lot lost money, and a lot of many hard years for those early movers, right? But now the times is ripe, as we say it, and it's at last we see a lot of great projects come online and being developed and being funded, not without challenges. I mean, we will live in the challenging times. I'm sure you will agree. Again, thank you very much for joining us. I think I said everything right. Do you think I forgot to say anything? Would you add anything to what I said?
Yes,
apart from, of course, introducing Derek and inviting him on stage, which I feel you're still trying to do, right?
Yes. Me and Amir on the background, we're trying to fix the issue, but I think it's the problem with his laptop. But he's probably gonna connect from his iPad in a minute. So what I wanted to add, thank you, Oksana, for the introduction. So we do this as a kind of value add to our audience, to people in our network. And we normally don't promote anything. We just want to make sure that you guys also know what we do, and you know that we are here to support you from the funding perspective. So whenever you guys have, if you're developers or you have access to projects, you can always reach out to us. I'm going to be posting in the chat section a link and my personal email address, my work email address, where you can send projects that require funding. So if you're a developer, it's pretty straightforward. We help you, get funding, and we work on success basis. If you have access to projects, but you're not a developer, or you can become our referral partner. We also, we have quite a comprehensive referral program that I'll be sharing a link to this page, which describes our referral program as well. We're also looking for new deal advisors for our team as well. We're growing our team. We have more projects than we can handle. We're growing quite steadily. Now, in regards to the technical part of this webinar, we have Q&A button, and we have section, and we have a chat section. Not to kind of distract and turn this into a chat where everyone is chatting. We have kind of disabled it. Here you can only chat with us as panelists if you have some questions. But we also have a Q&A section where you can ask questions related to Derek's presentation, also questions related to project submission. So once again, in the chat section, I will upload Derek's presentation, our QPQ presentation, and few useful links for you to follow. So that's for you to download. I will replicate it closer to the end of the webinar again for those who joined later. And so you'll see, some of you will see that it's doubled up. But again, we're also recording this webinar, so for those who missed it, we will send them recording. So now Derek is still not here, so let me just okay, he just messaged me. He's trying with his iPad now, so let's just give him another minute, and then we'll be ready to start. So in the meantime, perhaps Oksana, is there anything you want?
Just quickly. Yeah, so basically a bit of a background about Derek. So Derek is a CEO and product developer for Collier Wind. He is, he got about over 2 decades of track record in green energy space. And now in Collier Wind, basically his commitment is to create cutting edge breakthrough technologies, green energy technologies to solve the challenges that, the wind industry specifically faces. And then, of course, Derek, as part of his journey, has developed a wide array of green energy projects from microgrids to biomass and so on. So Derek, I'm sure will thank you very much for joining us. I'm thrilled and I'm happy that you managed to solve it. It's our greatest nightmare when we bring a speaker and we cannot, we have a technical challenges. We kind of learned with experience to somehow tackle those. So thank God you're online. Thank you so much for joining us. We're excited because we actually been a while since we spoke about wind, right, Vlad? And Derek actually has a very nice angle, and I agree that there are quite a number of challenges faced by wind industry, wind power. So we are very excited and looking forward to your presentation. All stage to you. I've been talking enough for today. Thank you. Thank you very much. We will get on stage.
Yes, so perfect. Well, great to have you here, Derek. Thank you again for making the time to present to our audience. So I'm adding Amira because I assume you joined from your
yes,
iPad. So there was some issue because Zoom upgraded things, and so Amira will be there flipping slides for you, and I'll be taking care of everything else in terms of chat, Q&A, and everything. So we're gonna, me and Oksana will come off the stage, but I'll be on the background. If you need anything, just ping me. I'll basically hear you, so I'll come back on. Okay. So guys, once again, if you want to post questions related to Derek's presentation, go through Q&A, not through the chat, and all the presentation slides and useful links I will be uploading in the chat section. Derek, the floor is yours. Thank you.
Thank you. Okay, so I appreciate you guys having me here. We have a very different approach to wind power. Amira, I'm not sure when you'll be able to start the slides. Oh, there you go. Thank you so much. Okay. So the current wind technology that's widely adopted is a 3-bladed design. Some advancements have been made in monitoring controls to increase efficiency and safety, materials to increase strength and lower weight, increase transmission efficiency and reliability, tower height. Sorry, I apologize. I need to move my screen. So all of these advancements, as well as the push for more development, has pushed the industry to go with larger blade sizes, increased tower heights, to try and increase basic system size. So, Amira, can I go to the next screen? Oh, sorry, the next one. There we go. The problem with what we're doing is we are trying to perfect a 93-year-old design. This was the first 3-bladed wind turbine ever in creation, and that turbine was actually quite effective. It was 32% efficient, which is a really high number when you consider the fact that today, the best we're doing is 38 to 40, and that's the best. And we have major issues with logistics, infrastructure limitations, as far as, when you're trying to transport turbine equipment through certain regions, the roads aren't built for it. So you have specialized rigging as well. You've got a 20-year useful life cycle because the structural integrity of the steel has been compromised due to the harmonic vibrations. You've got supply chain issues, which are really extreme when it comes to wind turbines. You've got most of your components coming out of China, and China is the leader in wind, but they're utilizing it, not necessarily sharing as much as we would like. And then you've got the power consumption from the grid. So one of the dark secrets about traditional wind power is they consume up to half their tag rating in any wind under 10 miles an hour. And the reason for that is they need to heat and cool all of their components, all the way down to the tower so that it doesn't rust out. You've got the motors that move the nestle into the direction of the wind. You've got the fact that you can't have the blade stall out for too long. You've got to backfeed the motor or the generator, turn it to a motor. All the safety equipment is all being powered from the grid itself. Then you've got the environmental concerns, which a lot of people assume is just birds and bats, but there's actually a much bigger concern about the environment when it comes to three-bladed wind turbines. And that's the fact that all of the blades are made of composite, which is basically a toxic material that at the end of its life is a nasty landfill problem. Okay, next slide. All right, here we have some of the images of the problems that I just discussed. The cost of installing a wind farm is pretty dramatic because what you see in front of you is a logistic nightmare. Just the fact that you're trying to move these extremely huge and heavy pieces of equipment poses major issues. And then at the end of their life cycle, or how about the fact that there's no set redundancy? So if you have a part fail, that's a major part. The repair could be so costly that the investment that you made in the original project could be out the window. And then you've got the end of the life cycle, which is approximately 20 years. And at the end of that life cycle, you not only have to deal with decommissioning, but many places force you to deconstruct. If you deconstruct, there's extreme cost to that. Unfortunately, you're not dealing with materials that are extremely useful after this life cycle, except for the steel in the tower, as well as the, maybe the copper and the generators, but it's still a fraction of what the cost to even tear down the system is. Okay, next slide. The other challenge is, as the wind turbine is interacting with the wind to actually capture the energy from the wind, it's acting on a singular plane. So as you can see here, the wind only interacts for seconds on the blade itself. 90% of the wind power passes by, it's never captured. Because of that, we have extreme limitations as to our efficiency and the usefulness of this device, simply because it's really not harnessing what we're trying to build it for. So, not to say this is an ineffective design, because obviously it is, but we're trying to push limits that are becoming dangerous at this point. and we're not doing it very effectively. You know, when we've got 93 years of development and only, you know, 5 to 7% of efficiency increase, and you're talking about an industry that is multiple billions of dollars a year, we should have higher expectations. Next slide. So with our system, it is a vertical axis wind turbine, but it's very different than any other vertical axis wind turbine. So the inherent problem with all vertical axis wind turbines is half of the turbine is always dealing with drag. That's reversing rotation, and it's creating a counteracting force, which is just robbing the entire system of efficiency and power output. So with ours, we have a diffuser system that directs the flow, as well as eliminates all the drag and refocuses the drag that would normally be seen on a vertical axis turbine and directs it into the power stroke of the blade system. This controlled wind flow allows us to harness low altitude and turbulent wind, which is extremely important if we're trying to put the wind market closer to the consumer, which I personally think is very important, because when we build the wind farm out on the ridge of a remote mountain, there's tremendous cost to the infrastructure needed to get the power from that wind farm to the people that actually consume it. And not only is there a cost, but there's tremendous loss from that turbine farm back to the consumer. So our diffusers act very unique against the actual blades of the turbine. They create a high velocity compression chamber, which gives us a higher potential energy to pull from, and it conditions the turbulent wind and actually stabilizes it so that it's easier to harness. Next slide, please. We have rigid framing around the blade systems. It provides protection while allowing optimum bearing locations, which is very important. So the other problem with vertical axis wind turbines is you have premature failures, because generally your blade system sits above the generator. So you have a huge moment on the generator, or where basically you have a tremendous amount of force or energy acting on this point where the generator connects to the blade system and is usually the support mechanism for the blades. So what happens is it's like having a breaker bar on the bearing. All of the energy is outside of the safe operating conditions of the bearing itself, where we take a different approach. Our bearings are above and below the blade system. So it's much like a traditional electric motor, where the stator is located between the bearings, just creating a very well balanced low friction machine. So long term, we have very little failure on the bearing system. The framing also allows for system expansion and the mounting of many different components. And when I say components, I mean different useful mechanical systems that can do other jobs, not just power production, like hydrogen production. So we have a system that we're implementing into our turbines that actually produces hydrogen on the turbine itself directly from the blades, so that there's no loss from secondary electronics. The other thing that this framing system does is it adds a high safety factor, because we're eliminating the rotating or the external rotating mass. We're confining it within our framing. And because of that, we're also one of the only bird-friendly turbines. So birds, when they see our turbine, they see a solid object, they'll fly above it, they'll kind of nest on top of it, but they won't fly into it. So it solves what can be a pretty major environmental concern, which has been stopping many wind farm developments. Next slide, please. So redundancy is something we pride ourselves in with our turbines. So not only do we have stacked turbines, but each of those turbines independently operates multiple power production units. So on the megawatt scale, we have each turbine running multiple power delivery systems. And we'll get into that further as we go. But having each one operate independently means not only do you have redundancy, but when you have maintenance, you're not shutting the system down at all. You're shutting a small piece of the system down. Because each system, each segment of the turbine has independent hydraulic pumps. Those hydraulic pumps are what transfers the energy from the blades to the actual power production into an accumulator bank, which acts as our battery system. So we're taking 100-year-old proven out technology from hydraulics. We're applying it to a wind turbine and making it so the wind turbine itself is simply the motor that turns the pumps, putting that pressurized energy into an accumulator bank, which is just a large pressure vessel. That large pressure vessel acts as a battery that has nearly zero degradation. So it doesn't degrade over time. You can literally shut the valves off and walk away for 6 months, come back, and you may lose 3% of the potential energy that's been stored. But you can turn the valves back on and you literally have nearly full capacity. Anytime you have redundancy on this level, you have completely isolated the rest of the system, so that, let's say there were a major failure on one of our turbine segments. We would only have, let's say it's 20 segments of turbine, you would have 1/20th of your turbine down, where traditional turbines, if there's a failure, you have one transmission, you have one motor, you shut the entire system down until fixed. Okay, next slide, please. So we've been, through our development, working on the smaller scale, trying to understand our technology better. And it's okay that you just went to this next one. It's perfectly fine. You could have stayed there. And so we've done projects all over the world, and we've had plenty of success. We've had plenty of failures. We learn from every failure, and we try to better what we do. But one thing that we've come to realize is redundancy is more than important. It's absolutely necessary. All of our systems are designed to be microgrids. We don't do any systems that are grid connected only. It doesn't mean that we can't connect to the grid, because we can, but even our megawatt systems are designed to operate as their own microgrid. And the megawatt systems are taking it to a different level. So because we're doing our own power storage through the hydraulic systems, it lends us some abilities that have never been realized before. So like the turbines that you see in front of you, these have lithium battery banks, and the power is stored within those banks, but obviously there's degradation, and there's maintenance involved with that. But there's, even through the power transfer, delivering power from the turbine into the battery bank is not always the easiest thing. It's not a fluid transfer of energy. Where with the hydraulic systems, it's seamless. When you pump that fluid, that energy is captured within the pressure vessel, and that's it. Then you use it on the backside through the drives. Next slide, please. We also deal with pretty extreme conditions, not only near water, but extreme winds as well. We've had the ability to test the limits of our small units, and we've seen what weather can do. Weather can be more than just abusive. It can be absolutely destructive. But these turbines, even through failures that we learn and we adapt from, they still operate very well. Next slide, please. Okay. So I don't know if the video is choppy on your end, but it's a little choppy from here, but you can see, how our systems operate, where the internal blade system is spinning within the frame and the diffuser system. And it can be very destructive if the system's not controlled correctly. But that just shows that the blade system and the diffuser system are extremely effective. And we generally, with these small systems, keep them very low altitude. So extremely turbulent wind, where other turbine systems just would not have the ability to operate. Next slide, please. So these megawatt systems that we've been working on, they're the first to offer
Derek, we cannot hear you.
constant power output, no matter the wind speed.
Derek, we lost.
Can you hear me now?
Yeah, we lost you for about 10 seconds. So if you want to just kind of repeat what you said.
Oh, okay. Okay, I apologize. All right, so what I said was we have the first wind turbine to offer base load. So base load is very unique, where the output of the turbine is stable. There are no variables. So when you utilize this hydraulic power storage, just like a lithium battery bank, it's able to deliver as needed. But with ours, what we're trying to do is create a stable, predictable output. So we want our turbines to be like any cogen plant, any natural gas, any diesel powered or gas powered, whatever it may be, output. So the turbine itself is the motor. That motor is running the hydraulic pump. That hydraulic pump is then storing hydraulic energy within an accumulator bank. Off of the accumulator bank, we have an array of valves and manifolds that feed the drives for the generators. So we're able to use all secondary equipment that's used in any region. So if we go into the Philippines, or if we go into Brazil or into South Africa, whatever equipment they currently use for power generation, we're able to couple directly to our hydraulic system and operate it no different than the existing utility company that makes the power that's currently being used. So that allows us to satisfy any regulations that are in any region, because really what we're creating is a motor that has a smooth power delivery for the gensets. These are highly efficient. They are quiet, they're smooth. As a matter of fact, all of the equipment that makes noise is built into soundproof shipping containers. That way we don't disrupt our neighbors and we don't get the environmental issues that we would normally have. That controlled power delivery allows us to actually bypass the need for inverters, because we're able to control the frequency and voltage. So we can use basic phase synchronizers to link right to existing transformers. Next slide, please. These are just a couple examples of what we're doing. So the hydraulic accumulators, they are standard equipment. They are built by Parker Hannifin. They're built by Vicker. This is very standard equipment. Then you've got the hydraulic pumps, same deal. The turbine system itself is just the motor. Okay, I'm seeing questions pop up. So as far as certifications go, each of our megawatt projects is built
don't worry about
similar
questions.
to how they build.
We'll address questions at the
Oh,
Q&A.
I'm sorry.
Yeah, I'll manage it as we reach the
I was
Q&A.
gonna say that was.
Yep.
I'm starting to see them, and yeah, that was
Yep.
okay.
Let's carry on with the presentation, then we'll have a Q&A session.
Okay, perfect. Okay, so we're basically just building the motor, which is the blade system, and then all of the components after are standard equipment used throughout many industries, very well proven, all certified. Next slide, please. So each of the layers of the turbine have, between 3 and 12 variable piston hydraulic pumps, depending on the size, the region that's being installed. It's all dependent on the predicted output from the turbine. And then if we find out that we installed a turbine that has more capacity that it could offer, we can add pumps when needed. Or if we find out the opposite, that we're adding too much, then we can take away some of that that power delivery from the blades themselves. So we have full adjustment on the volume of flow to maintain pressure through varying wind speeds. Each pump feeds the accumulator banks. It's controlled and stored without loss. And then we flow into the manifolds, which drive our drives for our generators. Next slide, please. And I apologize that I'm kind of repeating myself a little bit. So those hydraulic drives mount to standard synchronous generators, which we get from either WEG or GE or basically any company that is making generators for the region that we're installing the turbines. They're set to run at their optimum voltage, frequency, and output, which means we're able to tune the generator in to its highest potential efficiency. That controlled output gives us the ability to bypass, like I said before, the inverter system. And we're able to utilize ABB phase synchronizers to feed directly into the transmission system. Next slide, please. Okay, so as I stated before, those components that make noise are contained within shipping containers that are soundproofed. And this not only allows us to create a system that is quiet, but it makes installation very simple. It makes maintenance very simple. Any system updates are done seamlessly, and we can usually do it without any downtime on the turbine itself. So, or component replacement, same deal. And then the monitoring, we can monitor everything remotely from anywhere in the world, which is quite nice. Okay, next slide. So we have much more surface area than any other turbine on the planet. But obviously, square footage or square meters of any material has extreme cost, weight, and that issue has been solved by utilizing tension fabric, which is utilized widely in the construction world. The pictures and the images here are from the Denver airport. That roof is about 30 years old. And this material is per square foot or square meter, the lowest cost, highest strength. It's used for our blades and it's used for our diffusers. It also acts as a fuse. So if we're in the middle of a major weather event, we do not want our system just destroying itself. So what this structural fabric does for us is tears. So if there's a major weather event, it will simply tear at the highest energy point. And then we're able to go in after the weather event and replace the panels that have been torn. Even after they're torn, they will not just tear away from the system. They will stay in contact with the system so that we don't have debris going into our neighbors' properties. The repairs are very simple compared to a catastrophic event with a traditional turbine. And they come in many colors so that you can make people happy about the aesthetics. Next slide, please. Okay, this is a light image of the megawatt systems that we're currently putting in place. So this unit is approximately 130 meters tall, 100 meters wide, and each layer is completely independent of all the others. And this redundancy allows us to create a system that should have a 98% operating factor, even through maintenance. And we've developed this to have a very rigid skeleton that holds a trolley system for each of the turbines. Under each of the turbines, there's a friction ring, and that's where all the pumps and the electrolyzers are mounted and operate. Between each of the layers of turbine, there's a catwalk, and there's room for a maintenance person to go through and check all connections, look for any components that may be failing, and replace them easily. We also make sure that each component of the turbine weighs less than 600 pounds or about 300 kilos, so that we can easily utilize rigging that doesn't require a crane to do any maintenance. Even if we had a main structural tube that is within the framing that failed, we could replace it without shutting the system down. Next slide, please. So because the turbine spins within itself, there's no external moving parts, and we're utilizing very high safety factors. It allows us to take a megawatt turbine and put it into urban environments or rural, but you know, where the community actually lives. Next slide, please. So one of the things that we're doing right now is developing a few projects that are basically fueling stations of the future. So they're creating electricity to charge electric vehicles, but they're also creating hydrogen to power hydrogen vehicles. One of the unique elements of our turbine is we've been able to adapt the hydrogen electrolyzer system to the friction ring of the turbine and allow the system to seamlessly produce hydrogen at a rate more efficiently than any other electrolyzer on the planet, because we're bypassing all secondary electronics. So you're taking the kinetic energy of the wind, you're turning it into mechanical energy, and you're doing it directly into the electrolyzer system so that the losses are minuscule. So instead of 46 to 58 kilowatt hours per kilo of hydrogen created, we're more 42 to 45 kilowatt hours. Next slide, please. The other element to our turbine that is unique is during the phase of decommissioning wind farms, we're trying to make people aware of the fact that we can build these around structures. So because of the cost of decommissioning these turbines, we can actually mitigate some of that cost, but also utilize the infrastructure for the power transfer from the sites that obviously have good wind. They've already been permitted for wind turbines. And basically, this could be a solution if we could convince developers and government agencies to utilize this. It could possibly solve a lot of problems. Next slide, please. And that's just more of the same. Thank you. All right, now I'm excited to get some questions.
Thank you, Derek.
Yeah.
Very, very interesting. We have a lot of questions. We have 10 minutes left because we normally finish, the end of the hour. So we'll try to cover as many of them as possible, and the rest, perhaps we'll do offline, or send
Okay.
with the replay or something. First question is, how many turbines have been installed so far?
On the small scale, a few thousand, and then large scale, only a couple, but those are confidential. They're with a very influential group.
Sure. Okay. Are the turbines, are they TUV certified and bankable?
So the megawatt turbines are certified and bankable because they're built like a what do you call it? A hydro project. So their construction practice is what they are. So those turbines, DNVGL out of Germany certifies the design. We build the system because all of the components are certified. We get the design certification, and then we get the project certification.
Okay.
Now it's not your traditional certification that you would get with a normal turbine because we don't fit the mold. We've been trying for years to do what's necessary for them, but we honestly just do not fit the mold. So we've had to take a different approach with how the testing and certification is done.
Do you get them certified by different types of certification, or how does it? Well, you don't get them certified, so how does it work?
Well, no, they do end up fully certified through DNVGL. It's just I forget the terminology for the exact certification for wind turbines, but it's that's why I say it's more like how they certify a hydro dam. So you certify the design of the project, the components of the project, and you utilize the existing components that you utilize within your system. All of them are certified independently, then they're certified as an assembly.
Makes sense. And what are the models available for commercial operations?
Because the turbines have different layers, they're expandable. So
Derek, we lost you.
Anything from 1.6 megawatts up to
Derek,
8.
you're there. We lost you. We lost you there for about.
Sorry, can you hear me now?
Yeah, we can hear you now. We lost you for about 15-20 seconds.
Sorry about that. Can you hear me now?
Yep.
Okay. All right. I forget if
no, it's okay. We can move on to the next question. So you mentioned that was about the models, so the sizes, perhaps from.
Oh yeah, I hate to say it, but we can do up to 8 megawatts or even larger. I say that I hate to say it because honestly I don't want to build anything that large at the moment. So 3 megawatts is great. Up to 6 megawatts is still great. When you start getting past that threshold, then things get complicated. That's all.
And how does the LCOE compare with horizontal axis turbines?
Generally, the levelized cost of energy with our systems, even with the power storage in the envelope of the project, we're still 2 to 4 cents per kilowatt hour over a 25-year life cycle. But our life cycle of our turbines is well over 40 because all components can be replaced. The levelized cost of energy is dictated by a lot of different factors, with our systems, but one, obviously the wind speed, the complexity of the actual install. So if we're in a really remote location, now all of our components, everything we build for our turbines is small enough to fit in standard shipping containers, so that when we do installations, we don't have the logistics issues of a traditional.
Very interesting. All right, and the next question would be, so okay, let me have a look here. We have a Q&A because we have some questions in the chat and some questions in Q&A. So what is your opinion in terms of solar energy over wind energy with reference to efficiency? So is it, do you see this as more efficient?
It's higher power density for land area. So when you look at like in an island or a lot of Europe where land is very valuable and it doesn't make sense to cover vast amounts of land with solar, this takes up a fraction of that same space for the same output. To put it in perspective, a 3 megawatt wind turbine can put out in a 2-acre area or amount of space that it takes up, you could produce as much power as you would take up with about 35 acres to 40 acres of solar. So there's a tremendous advantage when it comes to power density.
Mm-hmm.
And because our systems are utilizing more or almost all standard equipment that's on the market, instead of each system being extremely customized and having gensets and transmissions and blade systems that are built very uniquely for each project, we allow the scalability of this to be very cost effective, because the companies that are in the sector that build the hydraulics, that build the generators, that build all the equipment we use, they're already scaled. All we do is place an order and we have the equipment we need.
Perfect. Okay, and how you can resolve the challenge of intermittency of power via wind energy for hydrogen electrolysis?
Our blade system operates down to 3 miles per hour. So as long as the system is located in a fair wind speed, you should always have some level of hydrogen production as well as electrical production. And just so you know, if we put in a turbine that has hydrogen production, there is also electrical production. And not only do we have both of those simultaneously, but our system, the reason it doesn't consume any power from the grid is because we have a secondary power system that powers all parasitic loads on the turbine. So any heating or cooling or aviation lights or anything like that is all powered by a secondary power system on the turbine itself. It has its own independent power storage and power delivery, because it's obviously not high tension. It's not, the traditional megawatt turbine that we build is going to connect to high tension transformers to deliver it normally. But with the secondary power system, we can deliver, 110, 220, whatever it may be, for the normal power consumption of any equipment on site. As a matter of fact, we can build in living space for a technician into one of the containers, and they have all the power they need right in that container.
Mm-hmm. Okay. There was a question about how they perform in the extreme weather, so whether they are able to fold up if impeding storms. But I think you already kind of explained on one of the last slides how it works, so we can perhaps skip this one. All right, and then next one, about offshore units. Are they hard fixed to ocean, or they would go through tethered floating system?
So what we are looking at as far as offshore is utilizing barges, old decommissioned barges that we can just mount to the platform. Hopefully utilizing spud barges where they have the spuds that come down and anchor to the seafloor. That way it doesn't necessarily have to be far out to sea. You can do it in, near a port just to, and it could be, because it's floating, it's mobile to a degree.
Okay.
So not that I'm going to recommend that we move around huge turbines on the water, but it is possible.
Yep. People are still hanging around, so perhaps we can take in 5-7 minutes more, and if you answer a few more questions, if it's okay with you.
Yeah, I'm fine with that.
Yep. So can you please estimate the rough current price per megawatt, or or target price you're planning to reach per megawatt for your units?
Okay, so it depends on a lot of factors, like anything else. But keep in mind that we have power storage baked into the project, no matter what. So keep in mind that this basically comes with its own lithium battery bank. On a project that is 3 to 6 megawatts, we're looking at probably, don't quote me on this, but about 3,000 per kilowatt installed. But actually 25 to 3,500 per kilowatt installed. And then obviously the larger the project, the lower the price per kilowatt installed. That's the advantage of these systems is we are utilizing traditional equipment, hydraulic equipment, electrical equipment on the secondary side. So if we're able to purchase in volume, then we're able to pass that savings on.
Oh, okay.
But also keep in mind, we are actually, we're not just selling turbines. So we're trying to be a part of the development, trying to retain some level of ownership to protect our technology. That's actually why we don't share a whole lot. Because I'm sure a lot of people are like, we want more. We want to see what they're actually doing. But we don't actually share that outside our doors because, it's not easy to protect technology nowadays, no matter what you do.
All right. And do you use gearbox in your system or not?
No, not necessary.
All right. Okay, about efficiency, I think well, perhaps this one, that we can cover. What is the tip speed ratio and RPM range, and is it considered a Savonius design? I'm not sure what it is. Perhaps you probably know.
It's actually it's a mixture of Savonius and Darius. So there is lift to our blades. So we're above 1 when it comes to tip speed ratio. And we can adjust for different regions, which we have done. So basically, we can have a tip speed ratio up to, about 1.5, 1.8. But we can adjust from 1 up. We like having a lower tip speed ratio and having a higher torque value. So we attain that by having a blade system that has a tremendous amount of surface area, but it's still very lightweight and has little to no drag. And it's really unique how the wind interacts with our system, because where a traditional turbine operates on a singular plane, we're working in a cubic factor. So when the wind enters our turbine, it interacts with the blade initially through the first part of the power stroke. And then as it flows in, it goes into the center of the turbine, but it follows the turbine. And then it actually interacts with the turbine on the back end of the rotation. about 180 degrees away from where it originally entered. So it actually, that's at that point is where the blade itself has the highest amount of lift. And it's really interesting how the fluid dynamics of the system works. It's very, very unique.
Mm-hmm. And what is the height? What is the height and footprint of about 1 megawatt turbine?
1 megawatt, I want to say it's approximately 70 to 80 meters on height, but even that's adjustable because we can adjust the width.
Mm-hmm.
So we can design projects that accommodate for different elements at each site. And all of our installation processes are standard construction practice. So we're not forced to have really customized technician training or anything like that, or custom rigging, or, you know, all of our framing is no different than what's utilized for building a large building or anything like that. That's all very standard.
Mm-hmm. Okay, and does the system, you know, can it operate basically in a low speed wind?
3 miles per hour, or 1.4 meter per second, something like that.
Mm-hmm.
Not only does it operate in low wind, but it operates in turbulent wind, which is actually much more important.
Mm-hmm. We got a question from Charlene about efficiency. I think you have covered this, right? And about future plans for equipment scale up in terms of the size, right? You said 3, 6, and you know up to 8 megawatt is okay, but for now you don't recommend.
And as far as efficiency for our system, you know, we ride in the normal range of traditional. So we're anywhere. It depends on what we do with our blade angle.
Mm-hmm.
But it comes down to about 34 to 37% efficiency.
All right. Okay. Well, perhaps one more question, you know, related to the wind speed. So, you know, you say 3 miles per hour is the slowest, right? But what would be the optimal, the best speed, you know, wind regime to operate with?
Anything over 7 meter, or actually anything over 6 meters per second is great. As far as average wind speed, and then if you're talking any given moment, as far as wind speed, if you're looking for optimum efficiency, you know, you're talking probably 8 to 10 meter per second.
Mm-hmm.
But you have to realize that when you're dealing with the wind, especially if we're trying to do it closer to urban environments, your system has to have the ability to operate in turbulent, low wind speed. So we pride ourselves in making a system that is very effective in these conditions. So we try not to dwell on a single moment. We're trying to accumulate as much power and store it as we can. That hydraulic system is a beautiful thing because it's a fluid transfer of energy. So when there's a wind gust, which traditional turbines cannot harness because the algorithms within their systems cannot keep up with the changes, we just simply have a fluid transfer of energy. So we are the only turbine system that is able to harness a wind gust, which might sound, you know, not that exciting, I guess, but that is a tremendous amount of energy that is normally lost. And we don't consume anything from the grid. We don't have parasitic loads coming from de-icing or anything like that. We're never trying to reposition our blade systems, whether it be the pitch or the direction. It's just not necessary for us. So we're not consuming off of, you know, the grid or the system, huge parasitic loads. So those are all added to our power output rather than, you know, being parasitic.
Makes sense. And just to wrap up, so do you develop your own projects? And if you are, do you look for, you know, development and construction, you know, CapEx funding? Because as you know, that's what we do. Or do you act as a pure kind of equipment provider?
We do a little of both. So any of our projects, we do kind of demand that we're part of it. But our clients generally don't mind that because this is new to everyone. So, and we discount for the element that we possess as ownership. So it's not that we're trying to be greedy, we're just trying to protect what we've created. And we do cherry pick what projects that we do. So
well, you know where to come. Well, you know where to come if you need funding.
Yes,
for the project finance. And so thank you very much, Derek. Very, very interesting presentation. Once again, you know, we appreciate you finding time and sharing this with us, with our audience. And very much, you know, appreciate everyone who managed to find time to join today. I uploaded once again in the chat Derek's presentation and a few other useful links for you guys to reach out to us and submit projects, become our referral partner. Or you know, so anything you need, there is also my email address you can reach out to. So that's it. You know, I really appreciate your time.
Would you be able to share my email with it?
I did, yes, I did.
Oh,
This in the beginning of the chat. Yes, Derek's email address is there. So you guys scroll up in case if you don't see it on the other messages, it's there. Well, thanks again, and yeah, have a great day. Cheers. Bye-bye.
You too. Bye, everyone.